Hi everybody, welcome to lecture 17 of Electrical Engineering 331. In this lecture we will continue to learn about Laplace transforms. In every single problem that we do, we will continue to look at tables 3-1 and or 3-2. So certainly you should mark those two tables in your books, and because it will be handy for you to be able to go directly to those tables. Okay, so the first example we'll do in lecture 17 is example 17.1, and it says to find the Laplace transform of x4 of t, which of course we'll call x4 of s. So find x4 of s if x4 of t is given by this formula. It's the second derivative of e to the minus 4t u of t. Now, the straightforward way to do this, and the way that you would probably think of at first, is just to go ahead and take the second derivative of this term, and then once you have that, then to take the Laplace transform of that result. And I extremely strongly encourage you to do that, to check the result that we are going to obtain. But we're going to take a different approach, and so let's see how it goes. Okay, well, entry number 7 in table 3-1 tells you about the Laplace transform of the second derivative. There's also a property in that table that tells you about the Laplace transform of the first derivative. And we will be using those entries substantially in the next chapter when we begin to talk about applications of the Laplace transform. We're going to find out that the Laplace transform will help us to solve differential equations. And we will be taking the Laplace transforms of derivatives frequently, particularly the first and the second derivative. So it's very useful to have formulas for the Laplace transform of a derivative or a second derivative. And this is our first introduction to that. So in this problem, since we have a second derivative, we will use the formula in the table for the Laplace transform of second derivative. And it says that the Laplace transform of the second derivative is s squared times the Laplace transform of the function itself minus s times the value of the function. Now this is little x. Little x is used to denote the function in the time domain, and capital X is used to denote the function in the s domain. In other words, the Laplace transform. So again, coming back down here, the Laplace transform of the second derivative of this function in the time domain is s squared times the Laplace transform of the function itself minus s times the function evaluated in the time domain at 0 minus the derivative of the function evaluated at 0 minus. And notice that this is the derivative. Since little x is in the time domain, this is the derivative with respect to time. So let's see how we would use this formula to evaluate this Laplace transform of here, the Laplace transform of this term. Okay, well, we're going to let this term in brackets, e to the minus 4t u of t, be x of t. And so according to this formula, we need little x of 0 minus and x prime of 0 minus. Well, x prime of t, we use a product rule, and so we get the first times the derivative of the second plus the second times the derivative of the first. And just as we have done before, when we have f of t times delta of t, that's just going to be f of 0 times delta of t. So, and f of 0 here, if f of t is e to the minus 4t, then f of 0 is e to the 0, which is 1. So we just get delta of t for this first term, and then the second term is minus 4e to minus 4t u of t. So that's x prime of t. And again, also, if x of t is equal to e to the minus 4t u of t, then we've already learned that the Laplace transform of that is 1 over s plus 4. So now we are ready to plug in to this formula the x4 of t is the second derivative. And so x4 of s, according to this formula, x4 of s, the Laplace transform of this second derivative of this, which is x of t, is equal to s squared times our x of s. So we have s squared times 1 over s plus 4 then minus s times little x of 0 minus, so that's minus s times, okay, x is right here, and when we evaluate that as 0 minus, that's just before 0, but remember that u for any time before 0 is 0, so this is just 0 there. And then we look at x prime. Well, we have calculated x prime down here, and x prime evaluated just before 0. Well, the delta function is 0 just before 0, and likewise, again, as we just said a moment ago, the unit step function is 0 for t just before 0. So x prime of 0 minus is also 0, just like we found that x of 0 minus was 0, so is x prime of 0 minus. So as we can see right here, so both this term and this term, the second term and the third term in this case, will drop out, and we're just left with s squared times x of s, where x of s is 1 over s plus 4. So we just have this first term, which gives us x4 of s is equal to s squared over s plus 4. And again, as I've already said, I very strongly suggest that you also try to get this problem, get the answer to this problem by computing the derivative first, the second derivative. Compute the second derivative of that first, and then take the Laplace transform of the result and make sure you get this same answer. So again, that example gives us a little practice using the formula for the Laplace transform of the second derivative, and this is a formula we will use a good bit more in the near future. Okay, example 17.2. Let's find the Laplace transform of t cubed u of t. Okay, now this one too is a problem where we could do it in a couple of different ways. We could just go ahead and evaluate this directly. We could plug in t cubed u of t into the formula for computing the Laplace transform. But the only problem there is it would be a little bit tedious, because we would have integral from 0 minus to infinity of t cubed u of t times e to the minus st dt, and so that would require integration by parts, which would not, that's a little tedious. So we're going to try to find an easier way to do this. And the key to finding an easier way is to look at entry number 9 in table 3-1. Entry number 9 says that the Laplace transform of t times a function is equal to the minus of the derivative in the s domain of the Laplace transform of that function. Now, I claim that this formula allows us to find the Laplace transform of t to the n times x of t. This is just the Laplace transform of t x of t, but I claim that by repeatedly using that formula, you can find the Laplace transform of t to the n times x of t. Well, how would this go? Well, let's do it for n equals 2, and I think you'll immediately see the how we played this game. So the Laplace transform of t squared x of t would be the Laplace transform of t times tx of t. Now then, think of this tx of t as being by itself. So we have the Laplace transform of t times a function. And according to this formula number 9, the Laplace transform of t times a function is minus the derivative of the Laplace transform of that function. So that's what we have here, is that the Laplace transform of t squared x of t is minus the derivative of the Laplace transform of t to the first power x of t. And that's just using this formula right up here, but in this case down here, t times x of t is playing the role of x of t. Okay, now we come down here and we use this property again. The Laplace transform of t x of t is minus dds of the Laplace transform of x, which is x of s. And so the two minuses cancel, and we have d squared ds squared of x of s. So we could continue this for any integer, positive integer value of n, and each time we would get another derivative and another negative sign. So it ends up giving us this formula right here, which is not in either of your tables, but which I think would be very handy for you to have. And it says that the Laplace transform of t to the n x of t is equal to minus 1 to the n times the nth derivative with respect to s of x of s. So let's see then how that would go and how that would allow us to find the Laplace transform of t cubed u of t. Well, we can see that that exactly fits this formula if n is equal to 3. So we say that that's negative 1 to the third power times the third derivative with respect to s of the Laplace transform of x, and what's playing the role of x here is the u function, the unit step, and we learned already that the Laplace transform of the unit step is 1 over s. So that's why I have 1 over s here. And so this negative 1 cubed gives us just a negative 1. And then the third derivative I'm going to write as the second derivative. I'm going to keep two derivatives out, but then I'm going to go ahead and take one derivative and operate on 1 over s. And the derivative of 1 over s is minus 1 over s squared. This minus can come out and combine with that minus to give us a positive. And so we're left with just d squared ds squared of 1 over s squared. Now, I'll keep one derivative out, but I'll go ahead and operate on this with one derivative. And the derivative of s to the negative 2 is negative 2s to the negative 3. Right here. And then we still have one derivative left out here. So the derivative of negative 2s to the negative 3 will be negative 2 times negative 3, or 6s to the negative 4. And there we have it, 6 over s to the fourth power. And again, I'll remind you that if you wish, you could check that directly substituting this into the Laplace transform formula, but that would require you to do integration by parts. And so I think that this is a considerably easier way to answer the problem. And then the final example for this lecture is the following. It says, find little x. Now remember again, little x is the function in the time domain. Capital X is the Laplace transform in the S domain. So determine little x of 0 plus and little x of infinity, given that the Laplace transform capital X of S is equal to s squared plus 4 over 2s cubed plus 4s squared plus 10s. Well, this is clearly different from any of the other problems we've been doing, but it is in the Laplace transform table 3-1, and these are referred to as initial value and final value theorems. For the initial value of the time domain function, we have little x of 0 plus is equal to the limit as s goes to infinity of s times the Laplace transform of x. And for the final value theorem, this x of infinity, what that means is just the limit of x of t as t goes to infinity. That's what that notation means. And it's equal to the limit as s goes to 0 of s times the Laplace transform of x. So let's see how this would be used in this case. Okay, little x of 0 plus, according to this initial value theorem, is the limit as s goes to infinity of s times the Laplace transform, s squared plus 4 over 2s cubed plus 4s squared plus 10s. So this s that we've multiplied out here could be used to cancel an s in each of the terms of the denominator, so that we get limit as s goes to infinity of s squared plus 4, the same numerator as we had here, but then in the denominator, notice that each exponent in the denominator has been reduced by 1, is now 2s squared plus 4s plus 10, because we use this s to cancel 1 power of s in each term in the bottom. And now, if we think about letting s get very large, then obviously in the numerator the dominant term is s squared, and in the denominator the dominant term as s gets bigger and bigger is 2s squared. So as s goes to infinity, this looks more and more like s squared over 2s squared, which is just 1/2. So the limit is 1/2, and little x of 0 plus would be 1/2 in this case. And then finally, for x of infinity, which again, remember that means the limit of x of t as t goes to infinity. According to the final value theorem, that's the limit as s goes to 0 of s times the Laplace transform of x. So again, just as we did up here, this s can be used to reduce the power of each term in the denominator. So we now have limit as s goes to 0 of s squared plus 4 over 2s squared plus 4s plus 10. And you can see as s goes to 0, the top goes to 4, and the denominator goes to 10. And so we just have 4/10 or 2/5. And so that would be x of infinity. So that example gives us a little bit of practice with the initial value and final value theorems. And that's it for this lecture. In the next lecture, we will begin the very important topic of partial fraction analysis of Laplace transforms, which will be very useful to us once we begin to use Laplace transforms to solve some differential equations. But that's it for this lecture, and so good luck.